So let's start with a scenario. Imagine you have the best AI available right now, one of these, brilliant large language models, and you ask it to do a million-step job, something huge.
Like what kind of job?
Something like building a skyscraper, bolt by bolt, or maybe managing the financial settlement for an entire stock exchange.
Okay, so mission critical stuff.
Exactly. Could you trust it to run completely unattended for all 1 million of those steps and guarantee zero errors?
Yo, not a chance.
Right. If you ask any developer today, that answer is a very quick and very firm no.
Yeah.
Modern AIs, they struggle with these long horizon workflows. Reliability just melts down.
It's a huge problem.
And that gap, the one between the flashy AI demos and truly trustworthy industrial-grade AI, that's the whole focus of the research we're looking at today. It's this maker framework from Cognizant AI Lab.
And what they've achieved here is, well, it's a major breakthrough. They took a standard, pretty inexpensive language model.
So nothing custom-built or huge.
Nothing huge at all. And they structured it into a reasoning engine that executed over 1 million sequential steps with perfect reliability.
1 million steps with zero errors.
Zero errors. The test they used was the classic Towers of Hanoi puzzle, specifically with 20 disks. Now, to solve that optimally, you need exactly 1,048,575 legal moves. It's a pure test of just, can you follow a very long plan without messing up?
Wow.
And this is such a critical lesson for anyone building automated systems. The success didn't come from a smarter model. It came from a much, much smarter system.
A system designed to break down the work.
And apply what the authors call ruthless error correction at every single step.
Okay, let's unpack that reliability problem because it feels a bit counterintuitive.
Right.
We hear that LLMs are, 99% accurate on a lot of benchmarks. Why does that fall apart over a long sequence?
This is math. It's just the math of compounding errors. You can't argue with it.
Right.
If you have a chain of dependent actions, so step 2 completely depends on step 1 being correct, step 3 on step 2, and so on, your chance of success just drops exponentially.
So that 99% figure.
Take that 99% reliability. That's a 0.99 success probability per step. If you need to get 1 million of those steps right in a row, the likelihood of success is 0.99 raised to the millionth power.
Which is basically zero. It's so small it doesn't matter. It means failure is guaranteed.
It's guaranteed. And that's the wall. That is the fundamental hurdle stopping generative AI from being used in these, high-stakes, mission-critical environments. The model isn't failing because it's not intelligent.
It's an architectural problem.
It is an inherent architectural flaw that just explodes over time.
And that's why the Towers of Hanoi puzzle is such a perfect test case. It's a known problem. It's deterministic. But that exponential growth in steps means that tiny 1% error chance will cause the model to lose its way, to, repeat moves or break the rules.
You just can't trust a single continuous thought process over 1 million steps. It's not built for it. So if we want AI that's safe enough for a power grid or for medical systems, we can't just sit around and wait for a model to be 99.99999% accurate.
We need a better architecture.
We need architectural certainty now.
Which brings us to Maker. The framework's whole starting point is challenging that idea. The problem isn't just that the model makes mistakes.
Right.
It's how we structure the work. Maker looks at this whole thing as an organizational design problem.
And that's where it gets really interesting. Instead of one super agent doing all the thinking,
Right, one genius violinist.
they use what they call a massively decomposed agentic process. They smash the huge task into the tiniest possible subtasks.
Okay.
These little jobs are then managed by very focused micro-agents, and the whole thing is tied together with these layers of really aggressive error correction. They're scaling the structure, not the model size.
That organizational shift is, I think, the key idea here. It looks less like software and more like a bureaucracy designed by someone who's extremely paranoid.
That's a good way to put it.
And they do this with 3 main ingredients, right? The paper outlines them pretty clearly.
3 main parts.
Maximal agentic decomposition, first to ahead by voting, and something called red flagging.
Right. So maximal agentic decomposition, that's all about specialization. Think about doing your taxes.
Yeah.
You don't ask one person to do everything from, finding receipts to interpreting tax code.
You break it down.
You break it down.
Yeah.
In Maker, these agents have these super narrow micro roles. For the puzzle, an agent doesn't think about the whole strategy. It just looks at the current board stake.
And its only job is?
Its only job is to propose the next single legal move and what the board will look like after. That's it. It's a tiny, dedicated, and very auditable little worker.
But even that microagent can still make a mistake because it's still based on an imperfect model, so you need redundancy. And that's where the voting comes in. First to ahead by voting. This is way more sophisticated than just, majority rules, isn't it?
Absolutely. This is the statistical magic. Instead of one agent making the call, you have multiple agents all sampling possible answers from the base model at the same time.
Okay.
And the system doesn't pick a winner until one candidate is ahead of all the others by a set margin, which they call K votes.
So K is like your certainty lever. You're not settling for a 5-1-49 split decision. You're waiting for a knockout.
A knockout. Precisely. What this scheme does is it mathematically decouples the errors. By demanding that clear consensus, the system pushes the probability of picking the correct action. Yeah. Extremely close to 1 at every single step. Okay. So those small, unavoidable errors from the base model, they don't cascade. They don't cause a systemic failure down the line.
And here's the bit in the article that really blew my mind. The engineering insight. Doing all this voting sounds really expensive computationally.
It does, yeah.
But the cost of all that extra sampling, it only grows logarithmically with the number of steps.
That's the crucial efficiency point. It's the economic game changer. You pay the small, manageable overhead at each step to get near-perfect reliability, and that cost barely goes up even when you scale to 1 million steps. You get trustworthiness without breaking the bank.
Okay, and the final piece is red flagging, the safety net. It seems incredibly simple, almost pragmatic.
It is. It's the ultimate sanity check. Red flagging is just an automatic process for throwing out outputs that signal confusion from the model.
Like what? What's a sign of confusion?
It could be a really long, rambling answer when you're expecting a simple command, or just, malformed data that doesn't fit the format.
So it's like a spam filter for your own agents. If the output looks weird or messy, you just toss it out and try again.
You toss it and resample. It's a cheap and effective way to stop a rare but correlated failure from poisoning the whole voting process. It's just good, classic software engineering.
So let's just go back to the benchmark for a second. The scale of it is it's staggering. 20 disks, 1,048,575 perfect ordered actions, a small model orchestrated by Maker. 0 errors. It just proves the system works.
It absolutely does. And there was a great analogy I saw from a Reddit commenter that just nailed the core idea.
Oh, yeah.
They said comparing Maker to a single LLM is like comparing a coordinated professional orchestra to a single solo violinist.
Oh, that is a powerful image.
Isn't it? The solo violinist might be a genius, individually brilliant, but they can only handle so much complexity before they slip up.
But the orchestra can handle Wagner, this huge, complex, long-running piece, and they do it reliably.
Because the system coordinates lots of imperfect players. That coordination, that system, that's Maker, is taking an imperfect component and stretching its reliable horizon by orders of magnitude.
And this really forces a reframing of how we think about AI scaling. For years, the focus has been on scaling up parameters, getting more training data.
Bigger single models.
Yeah, bigger single models. And they're great for one-shot creative answers, but they are notoriously brittle on these long operational workflows.
Whereas the Maker approach flips that. It scales the system, the decomposition, the agents, the voting rules. It requires more upfront engineering, for sure.
Sure.
But for critical infrastructure, that trade-off, certainty over creative flair, is exactly what you need. Architecture beats wishful thinking. Every time.
But we have to challenge this a bit. The Towers of Hanoi, it's a perfect puzzle, a deterministic, closed system. How does this apply to the real world?
That's a fair question.
Where APIs fail, data formats change, users do weird things. Isn't that comparison almost irrelevant?
It's a necessary challenge, and the authors agree that the real world is messier. But they argue that the architectural lessons are highly tortable.
How so?
Well, you look at any complex commercial process, a robotic assembly line, a big document review workflow, those systems already have discrete steps. They have boundaries.
Okay, I see.
So you can still decompose the tasks aggressively. You can still have voting agents compete in each step. And you can still put that ruthless error correction at the edges between the steps, whether that's checking an internal state or, checking the status code from an API call.
So for the developers listening, the pattern here starts to look like a kind of a microservices architecture, but for AI.
That's a great way to think about it.
So what are the most practical principles we should be borrowing from this right now?
First, think in micro roles. Design your agents for the smallest meaningful unit of work. It makes them way easier to test and reason about. Second, introduce voting early for any step where an error would be really expensive.
Because it's cheaper than we think.
The logarithmic scaling makes it surprisingly cheap. And critically, separate your creative planning agents from your execution agents. Use the big creative models for the high-level strategy.
And then use these maker-style micro-agents with all the tight checks to actually carry out the plan.
Precisely. You get the best of both worlds.
This idea of smarter systems, not bigger models, just feels like a profound shift.
It is. Because you don't actually need the biggest, most expensive, cutting-edge model to do these long-horizon tasks reliably. You just need a model with decent per-step accuracy.
And then a framework to squeeze extreme reliability out of it.
Right. It completely changes the economics. Teams can get much more predictable results and for lower operational costs by focusing on robust architecture instead of just chasing the next biggest super agent.
So if we pull this all together, the real headline isn't that an LLM solved a puzzle. It's that a modest model, wrapped in a really smart architecture, delivered a million-step sequence perfectly.
The future of safe AI, the kind we can actually trust in a hospital or with our finances. It's not going to be one single genius that never makes a mistake.
It's going to look a lot more like Maker.
A lot more like Maker. Many narrow agents, extreme decomposition, and aggressive structural checks on every single link in the chain.
So let's leave you with an action item then. Take one critical, maybe brittle workflow in your own stack, that script that fails just often enough to be a real headache, and ask yourself, what would this look like if I rebuilt it Maker style?
You can start small.
Yeah, just wrap that one script in a microagent harness and add some redundancy. See what happens.
Because long horizon reasoning isn't going to come from just being optimistic. It's going to come from engineering discipline. And so the provocative thought we want to leave you with is this.
Okay.
Since this paper shows that smaller models can be made extremely reliable with the right system design, how might that change the economic incentives for AI development? Could it shift resources away from the expensive race for raw model scale and toward more creative, robust system architecture? That's the question for you to explore next.